To begin our work with area, we're going to start with sigma notation. Now, this is just a concise way to talk about sums. So it's a notation to really help us as we go through and set up different problems to add lots of numbers together. So for instance, in this notation, we begin with the lower number, we end with the upper number, and then what's happening is you're plugging in, beginning with this lower number, all the integer values as it leads up to this. And this expression here has variables that are k's, which are called the index of summation. So what happens essentially is you plug 1 in for k and get that value from this expression. Then you plug a 2 in to k to get a new one, and a 3 and a 4, and so on until you get to n. And each one of those terms is added together. So at the end of the day, when you get done with this, you add them all together, it just equals a single value. So for example, a very simple one could be k from 2 to 6 of k. And that just means that, again, we're going to plug a 2 in for k, which would be a 2. Then we plug a 3 in for k. Then we plug a 4 in for k. And then a 5 in for k. And then lastly, because 6 is the last number, we'll put a 6 in. So that's just adding the numbers essentially from 2 to 6. Now, when you put all those together, of course, it does give you a number, right? We got 5, another 5, another 10. So this is going to give me a sum of 20. Now for our next example, it's a little bit more involved, but again, we're simply plugging in the values from 0 all the way up to 4 into k, and those are integers, of course. So plugging 0 in gives you 1 divided by the square root of 1, which is 1. If I plug a 1 in there, that'll give me 1 divided by the square root of 2. If I plug a 2 in there, that's going to give me 1 divided by the square root of 3. Plugging 3 in gives me 1 divided by the square root of 4, which would just be 1/2. And then plugging 4 in would give me 1 divided by the square root of 5. Now in this case, if we do sum it up, the answer is not rational, but the point is, whether it looks very simple or complicated, you're plugging values, from the bottom number to the top number, each integer value in for k. Now, as we do this, we want to talk about some basic properties to help us be more efficient with our time and energy. So the first thing, of course, is that if we notice that the expression involving k is being multiplied by a constant, we can actually distribute it out and do the sum after that. So for instance, this problem right down here would be the same as multiplying 3 times the sum, where k goes from 1 to 10 of just k squared. Now, if you're wondering why that would be helpful, oftentimes these sort of things maybe have more efficient formulas, so I can go ahead and punch this up, and once I get done with that, multiply it all by 3. And it should make sense, because if every single term was multiplied by 3, you could easily factor it out and then multiply that times the entire sum. So this is essentially just factoring. Now, the same is true when you have two different kind of terms that make up the inside part of the sum. So if you have two different pieces here that have expressions of k in them, you can actually individually figure out their sums and then add them together. So what that looks like down here would be something like, over here we have 2k, so that could be 2 times the sum going from k equals 3 to 15. And that would be just of k. And that's, of course, using that previous property as well. But then we subtract whatever the sum from k goes from 3 to 15 of 6. And again, this helps us kind of divide and conquer. There are sometimes easier formulas to tackle these sort of things, so by breaking it up and doing each one individually, it can make our work a lot easier. Now, in order to help us do the different summations, we have some formulas here to help us out. Now, these specific 4 are chosen because oftentimes the situations we're going to be in are going to be modeling polynomials. And polynomials have things like numbers, x's, x squareds, or even x cubes. And so these are going to offer us shortcuts, especially when the number of values we're adding together is really large. So our first summation formula is adding constants. So we have the same number that we're adding over and over and over again n times. Well, that's just the definition of multiplication. So the way we do this is we take the constant value that we're adding over and over and over again and just multiply it times n, the number of times we're adding it. There's no k in here, so we don't actually plug 1, 2, or anything into that. We just say we have this value c and we're adding it over and over and again n times. Now our next formula is just a k, which means plugging in 1 and 2 and 3 and so on. This is just the sum of the counting numbers, right? This is 1 plus 2 plus 3 plus 4 and so on, all the way up to some number n. Now the way you do this calculation is you take the number you're adding to, you multiply times the next number, and then you divide by 2. And that offers us a quick shortcut to make that work. Now, in order to calculate the sum of squares, in this case 1 squared plus 2 squared plus 3 squared and so on, it's similar in that you take the number you're adding to, you multiply it times the next number, but you also multiply that times twice the number you're adding to plus 1. Then you take that entire product and divide by 6. So it's a little more complicated, but does definitely offers a quicker, easier way to add the sum of the squares of numbers. Now for our last one, we're adding the cubes of numbers, 1 cubed plus 2 cubed plus 3 cubed. And this is actually kind of interesting because we're going to use the formula here for adding the sum of the numbers. So n times our next number, n plus 1 divided by 2, except we're going to take the sum of the numbers and then take that all together and square it. So again, a very interesting relationship is that the sum of the numbers squared is equal to the sum of the cubes of the numbers. Now, it also makes it easier on us because we have a little less to memorize. But again, what we care about is having these nice formulas to offer us quick, easy ways to evaluate these sums. Now, one very important thing to note about all these formulas is that they only work when your lower limit of summation is 1. So the assumption with all of these is that as you're adding, constants, or especially like, numbers, the squares of numbers or cubes of numbers, is that you always begin with 1. So again, if this is not k equals 1 here at the bottom of all of these, then these formulas don't apply, and you have to make adjustments to make that the case. So let's see these in action. So if I'm going to find the sum from 1 to 30, of k, that just means 1 plus 2 plus 3 plus 4 all the way to 30. So the shortcut way of doing that on this one is to say, well, we're ending with 30, and then we'll multiply times the next number, which is 31, and then simply divide that by 2. So when you do that, you end up with a sum of 465, which again, I think we can definitely say is a lot faster than manually adding all those numbers. Likewise, if we want to add the numbers from 1 to 30 of the squares, that means what's going to happen is we'll take the top number 30, multiply times the next one, then multiply times 1 plus twice 30, so it'll be 60 plus 1, so 61, and then divide the whole thing by 6. And doing that calculation gives us 9,455, which again is much faster than manually adding all those squares. Now, what it looks like here for cubes, remember, is the same as we did for just adding the numbers. So we'll have the 30 times 31 divided by 2, but then we take those numbers and square it. And when we do, we get a much bigger number because essentially you're taking 465 and squaring it, and this gives you 216,225. Now, what this is going to look like in practice is going to be us dealing with polynomials. So as you can see, we're going to add the numbers from 1 to 16 of this cubic. Now, what we're going to do, of course, is use the properties and these rules here to help make this much easier. Okay, now I'm not going to rewrite them, but we are doing each one separately, and especially with this one right here with a 3, we're going to put that 3 out front. So again, we're going from 1 to 16 and using the formulas for each one. So for k cubed, that means we're going to use the formula here for cubes except ending at 16. So that means it'll be 16 times the next number 17 divided by 2, and then we take that whole thing and square it. Now the next one's going to be 3 times the rule for squaring, because again we put that number out front, and since we're squaring it, that means it'll be 16 times 1 more than that, so that's going to be 17, times 1 more than twice that number, so that's going to be 33, and then we take that whole thing and divide it by 6. Now the next part is just k, so that's just adding the numbers from 1 to 16, so that's just going to be 16 times 17 divided by 2. And lastly, we have a minus 8. So we'll subtract the 8, but remember, we're basically adding negative 8 16 times. So we just multiply that times our n. Now again, this would be very complicated to manually plug each number in, but just plugging this formula in offers us a much quicker way to make it happen. So when you type all that in your calculator, you'll get 14,016.